Alrighty, so we have one student here who's not actually a student, and that's too bad. But anyway, I thought I would go over the quiz. Quizzes, here we go. And its answers. I believe everyone's taken the quiz, so we can go ahead and go through this. So, the first question, MPI is based on sending messages through a network. Which of the following information is not necessary to send and receive a message? And the answer is the type of network, because MPI handles that. You don't have to handle that. However, you do have to tell MPI how much data is being sent, where it's being sent to, and where the data is located. MPI send and MPI receive are both examples of a point-to-point communication, whereas we have the opposite answer. So, I mean, if you got one wrong, you probably got both of them wrong, but I don't think anybody did. So MPI broadcast and MPI reduce are examples of collective communications where everybody is working together. Then we have a programming fragment here. So we have, if my rank is equal to 0, then I want you to do a broadcast followed by a send, or else I want you to do a receive followed by a broadcast. And we're assuming that there's only two processors, so there's only two options here. And the above MPI program fragment is not correct. And the question is, why? And the answer is not because MPI send is synchronous. It could be synchronous. It's blocking is the term that should be used here. Because the tags are mismatched, you'll notice we just use tag, and so they can't be mismatched. Because processor 1 blocks an MPI receive, while P0, processor 0, blocks an MPI broadcast. Or because processor 0 is the root of MPI broadcast. So the broadcast here, we have to have a root, which is fine. There's nothing wrong with that. However, the answer is this one, because the broadcast, you have to assume, is synchronous. It's completely blocking. It's going to sit there and wait for everyone to call the broadcast, whereas the receive, in this case, is going to sit and wait for the receive to happen. And the receive is waiting on the send, which isn't happening because the broadcast is waiting on the broadcast, which still isn't happening. Anyway, you can work through that if you got it wrong. So what could be done to fix the above fragment? Stop using MPI, that's not really an option. Making P1 the root of the broadcast also doesn't fix it. Or we could switch the order of the broadcast and the receive. And there's actually two answers. Or we could use the asynchronous communication. Either way would work. So if we switch the order, we'd have a broadcast matched with a broadcast, and then the send matched with the receive, which would fix that problem. Then the purpose of the Cartesian communicators is, one, to make it easier to work with Cartesian problems. Okay, we want to take our processors, if our problem is a Cartesian problem, okay, we have nice straight lines in X, Y, and Z, then it makes sense to take our processors and arrange them in a similar fashion. And so it makes it easier to work with these problems, and it could allow for more efficient use of the hardware, because if the hardware itself is arranged in a Cartesian fashion and the MPI library knows about that, then it can make things easier All right. Now, which of the following is not an advantage to using asynchronous communication? This one should be pretty simple. Anything that increases program complexity, typically not an advantage. So, you should almost always prefer collective communications over trying to implement the same thing yourself. The answer to that is true, unless you really think you can do it better and without bugs. So, and then the question is, what is network latency? And the technical definition, the amount of time it takes to send a message of 0 bytes. So, that's kind of your ping I showed you before. When you're pinging something using your speed test, is how long does it take for a message, one single electrical impulse to travel from A to B, basically, is your latency. And then why is it generally better to send one big message as opposed to many small messages? And the answer is because each small message pays a latency penalty and doesn't use the full network bandwidth. So if your network can send 100 gigabytes of data, which is a kind of ridiculous network, but if it can send 100 gigabytes of data and you're only using it to send one little electrical impulse, you're not using it. It's like you have a 12-lane highway for 4 cars in the middle of Montana. You know, it's kind of ridiculous. So anyway, that is the MPI quiz. And let's see here. What else? There was something else I wanted to go over, I thought. But anyway, I've got almost all of the Project 7, the N-body problems. I don't know what happened with the weak scaling. I don't know why we are getting bad answers for that. I thought about it for a long time, tried to work through the math, tried to come up with new definitions of what our work should be, and I'm not sure why it's doing what it's doing. Again, I'm not an expert on this. I do mostly Jacobi type problems instead of N-body problems. So, got something stuck in my throat. So yeah, I don't know why that didn't work. Anyway, so today I'm going to continue talking about C++ exceptions and kind of how we use them effectively and correctly, because they can cause problems. But the C++ community, they say it solves more problems than it creates. So we'll go along with that. So last time we talked about error handling and how we handle errors in our code and things that are wrong. And so this is kind of your C way of doing things with your return codes. Of course, this is an example of a bad error. This is not helpful to the end user unless you have a Windows manual or you have, I don't know, a Windows expert on hand, which most of us are not. So exceptions are kind of a way to get around that. Not to get around it, but approach it in a more usable manner. Throwing an exception, this is very, very important. Calls the destructors of all objects that are in that function where the exception was thrown. This is called unwinding the stack. It cleans up your memory for you. So that takes care of the memory issues that often show up in C like languages. And but the other thing that you can do with exceptions is you can pass a lot more information, whereas in the old way of doing things, all we could really do is return an integer. Say, oh, we got error 4. If we got a little fancy, we could use enumerations and say, okay, we returned an error square root negative. Okay, so that's slightly better. It tells us directly that this is a negative value in the square root. as opposed to something else. But the exceptions allow us to throw anything we want. We can throw a string with a big long line of text explaining exactly what happened, or we could throw an integer or a double. But the most useful thing is you can actually throw classes. And so you can have special classes designed for these situations. And as usual, the C++ standard library has its own version of this, and they call it standard exception. All right. So the standard exception obviously is a class meant entirely for exceptions. It is the base class that is used for all exceptions in the standard library. It contains a virtual member function called what. Okay, and what returns a string, a pointer to a constant character, describing why the exception was thrown. And so here's an example. First off, on the left here, we have an example, I didn't cover this last time, of multiple catches. So we can catch an integer, we can catch a character, and then we can catch a ... which is everything else. Okay. And so that is an example. You can throw multiple types of things, and so you can say, okay, we threw an integer, which means this thing happened, or we threw a character, which means this thing happened. And then on the right here, we have an example of throwing a standard exception. And so we catch the standard exception, but we can catch it by reference here. And what that allows us to do is that we can now throw anything that is inherited by or inherited from the standard exception. And then we can just call e.what, and it will spit out a nice little string telling us exactly what happened. And if your inherited exception allows this, you can actually modify the exception. And so you can say you have several levels of functions, okay? And you throw an exception down here at the bottom. And so that goes up to the next function, and it can actually modify that, give it maybe a little more information as to the state of things or why things went wrong, and then rethrow the exception back up to the next level. And you do that, I didn't put it in here, but just by putting an empty throw statement at the end of the catch block here. And you can rethrow it, and the next function can add its information, and rethrow it, and the next function will add its information until you get to the top and you have a nice long description of what has happened. The standard exception by itself doesn't do that, but you can definitely, it's a lot more robust way of handling the errors and understanding what went wrong. Anyway, so here's a basic list of every single class that inherits from standard exception. And I'm just going to point out some of the big ones. First off, bad alloc. This happens if there was a failure to allocate memory. If the operating system refused, if you're out of memory, or something terrible happened, then the new statement will throw a bad alloc exception. And that's the biggest one. Another important one is bad weak pointer. This is thrown by the weak pointer. If you try and turn it into a shared pointer and that object has been deleted, it'll throw this particular exception. And there's a lot of other ones, but those are kind of the big ones up here. And anyway, so what's really important about the bad alloc one is that anytime you use an operator new, you could have an exception thrown, and that's something you have to account for. You have to account for the fact that every function could throw an exception, and so here's a problem with that. So Here we have this function. I just pulled this off of Stack Overflow somewhere. First off, we have an if statement with a comparison in here. This is very simple. It can't throw, can't fail. Here we have a simple incrementing operation. This also is simple and cannot throw. But here we have a pointer. We have some class called X, capital X I should say, and now we have a pointer to that class called little x. And we are allocating memory using the new operator. And this could throw. All right. Then we have a t.list. Apparently it has a list in here, and we're pushing back x, this pointer x, onto this list. And this also could throw. And then we say x, do something that can throw. That's kind of a very verbose function description, function name there. And obviously this one can throw. So here's the question, is what happens if number 3 or number 4? Why is my pointer not working? Well, okay, I have no pen. I don't know why. What happens if I push this button? Okay, well, the mouse works, but the pen doesn't. Great. Okay, so what happens if number 3 or number 4 throws? Basically, if these throw, it will exit this function, at which point we have a pointer to some memory here. And that pointer gets lost. Okay, because it's a pointer, the destructor of capital X does not get called. And so this resource or this memory will leak. The capital X object is still there in memory, but we haven't deleted it properly. So how do we fix this? And the answer is we use a smart pointer instead. And so we have this smart pointer, and we give it this new object to point to. All right. And so if anything after that throws here, then the destructor of the unique pointer will be called, and the destructor will then delete the memory that it's pointing to. So anyway, that solves the memory leak issue. And this is what's called RAII. I don't really understand the title. Apparently there's a lot of other names for it too, but this is the one that's stuck. It's called Resource Acquisition is Initialization. Basically what it means is you want to encapsulate all of your memory. And I talked about memory management before in 2 other lectures. But by doing this, we get what's known as exception safety, meaning we're not leaking memory. So every function should have what's known as an exception safety guarantee. And there are 4 types. The first exception safety guarantee is none, meaning the function could throw and it will leak or throw up or melt down your refrigerator. Okay? And that is the type of guarantee that this particular function gives, because it is not doing things properly. You'll notice here, each line here shows the guarantee for this line. Okay? So we have then the basic guarantee. The function could throw, but it will not leak, and all the objects will be whole, meaning they will be in some state where they are not dead or dying or corrupted in any fashion. All right? The strong guarantee is that the function could throw, but it will not leak, and all objects that have been passed into the function will be unchanged from when they entered the function. So that's different from the basic one in that all the objects will be whole, meaning they won't have nands or they won't have horrible a state, but this one means that they will be unchanged. And then there's the no-throw guarantee, meaning the function will never throw an exception. And so going back to here, this first line is a no-throw. Every operation in here is a no-throw operation. They're just basic comparison, and this is a basic incrementing thing. Now, the new operator has what's known as the basic guarantee. It can throw in either the memory allocation or the constructor for X. Either one of those could throw. And that has a basic guarantee because the X constructor, what happens, it's like the X class is placed into some sort of zombie state if the constructor throws. All right, so then we have the list pushback. This has a strong guarantee, meaning that the pointer X will not be modified if pushback throws. And this one has a basic guarantee, okay? But when you put them all together in this order, without using the unique pointer, this function has the none guarantee. It has no guarantee because the resource could leak. Anyway, basic is pretty easy. If you want to make sure you always have a basic level of exception safety, use your smart pointers, use your containers, your vectors, your lists, and so on to dynamically allocate memory. Rule number 2, never, ever, ever write a destructor that could throw. Okay? Destructors should always have the no-throw guarantee. Rule number 3, always read the documentation and note their guarantees. And these rules should, in general, give you the basic guarantee. Writing code for the strong guarantee is a lot harder to do and can be more expensive, and there's lots of examples online if you want to pursue this study. Often, however, the strong guarantee is easy to come by because your operations are simple. So anyway, just talking about us, okay, as students, we usually don't need to worry about this. We're not writing production level code. We're not selling this to anybody. We're not complaining to anybody. No one's complaining to us. But I wanted you to be aware of this stuff, especially if you do go into a production environment. Coding is becoming far, far more common for everybody. So I wanted you to be aware of this. And, if you see it mentioned, to not be like, what the heck is going on? What are they talking about? I want you to at least understand the basics. Now, C++ uses what's called the zero-cost exception model. And what that means, excuse me, something in my throat, is basically that if no exception is thrown, then there's no runtime overhead with it, other than, of course, the quick check to see if you should throw the exception in the first place. But if the exception is thrown, then the stack unwinding procedure takes a significant amount of time. Not to mention, you completely lose your place if you're not trying and catching things properly. But if you ever run across that term, that's what they mean, is that the exception will not, the presence of the exception safety code doesn't actually slow your program down unless the exception is thrown. Does that make sense? Hope so. And then Ted here wanted a quick thing on what assertions are. So let's just add this in. Assertions are kind of a very, very simple error checking method. Okay, and it's done using the assert command. And inside of here, you have to put some sort of true or false statement. Okay. And so this is something we could actually use in our square root function. So let me go here and just Notepad++. Just download this real fast. Da, 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 da. Yes, 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 yes. Okay, so let's change the language here to C++, and we'll make the font size bigger. So if you type assert, you see, okay, not a Boolean, but an integer expression. 0 being false, anything else being true. So basically, we could use this for our square root function that we were doing earlier. So and we'd put it in here like so. We can assert that x is greater than 0. And then, of course, we return the square root of x. Okay. And so what this does is the assertion, if the assertion is false, it will completely abort your program. It just closes everything out and stops. It's very useful for checking important information. I should say inputs to functions. If an input to a function has to follow some sort of guarantee, such as in this case, it has to be positive. Of course, 0 also counts, so we technically should do a greater than or equal to. However, that doesn't provide a lot of information, and there are ways around this. For instance, you could do something like this. And this is legal. The string always evaluates to true. And so if this is true, then we get true and true, which is true. But it does give you a slightly more information, because then the assertion will get printed to the screen, at which point you can see, oh, negative value in square root. Okay. There are other assertion functions that you can. A lot of people kind of implement their own assertions that do a lot more stuff. But the basic idea is that these things, this particular statement is held, that's the word, inviolate. It has to be true. And if it's not, your program it can't function anymore. And so they get used a lot in some libraries. Eigen uses them. I personally prefer exceptions, and there's a lot of different philosophies on when you should use an assertion versus an exception. So anyway, that's the basic assertion. There is one more type of assertion in C++ now. It's called a static assert. This is when you're dealing with templates, and you want to make sure that something is true. I use static assertions. These things are evaluated at compile time. They will, if they turn out to be false, they will freeze or stop the compilation. So I use them in my array classes to make sure that the right number of parameters are being passed in. And so you do something like, I think it's like rank is equal to something else. Size of, that's what it is. Size of ... IDX ... something like this. And the compiler evaluates those and makes sure that they are true at compile time. And so they don't cost you anything at runtime. An assertion gets evaluated every time the function is called, and so that cost can add up, whereas this is a one-time compile, one-time cost at compile time. So that's kind of your basics of assertions. If you ever see those or run across them, that's what's going on. So anyway, that's all I have for you today. Tomorrow, I'm planning on going over Vim, since I've had a request to talk more in depth about Vim. And then I was thinking about going over Git on Thursday, but we'll see how that goes. Anyway, so hope everyone's doing good. We have a couple more projects that are still coming in, and I haven't heard if anyone wants to do the extra credit project or not. So let me know if you do, and let me know if I can take a vacation, I guess. Anyway, we'll see everyone later.